Hey everybody, how are we doing? We got Jillian here, we got Adelaide here. We're gonna go over some. Oh, wait, Brian's talking in the background. There we go. Brian's no longer talking in the background. This means we're streaming. Awesome. So we could go over the question about Chapter 9, homework about people, classifying people by gender and political party. Definitely. Let's go check that out, Jillian. And Mubot is awake, so let's give out some points. Let's go get that Chapter 19 question about gender and political party. Now, this one, you can work by hand, which is a lot of work, but it's much easier with jump. So we want to use jump for this. Let me close out some jump data sets I got open. File, save as. Okay, close out there. And let's get a new jump data sheet. You'll be seeing everything here in a second. Jump 16 on my computer now. Finally got jump 16. I've been using jump 15 for a little bit and had trouble downloading from jump 16 from UT. The homework question about political party and gender. And replace questions. We're almost there. We'll chill music while we go there. And here we go. Political party and gender. Let's go check it out. So this is the homework question about political party in general. We'll probably do all the homework right now. Just put the homework in this video so people can see it and work on it. So is this the homogeneity test or the chi-square test of independence? Now, the chi-square test of independence is what we're learning in this chapter. So that's the answer. The chi-square test of independence tells us if gender is independent of political party. That's going to be the null hypothesis. The alternative would be gender is not independent. And I want to point out that you just put independent between these words right here. So all you're going to do is write that they're a great job, Jillian. 100 points, following along. Love it. Independence right here is what we're testing. Are the two variables independent of each other? Which literally just tells us the null hypothesis. We're going to start out with the belief that they are independent. And I like to write the alternative that they're not independent. I think it's the most clear way to write it is the null being that they are independent and the alternative being that they're not independent, because then it's complements. They're either independent or not independent. Now, what does independent mean? It means if you knew somebody's political party or you knew someone's gender, you would know nothing about the other one. Like I know someone's male. Does that tell me anything about them being Democrat, Republican, independent? Independent means knowing someone's gender tells you no information. You would know nothing about their political party. Not independent means there would be an association. So sometimes you see words down here for not independent, like associated or relationship. Knowing someone's political party would tell you something about someone's gender. So that's what that would mean right there for the alternative. Is this count data? Count data means that both variables are categorical, and gender is categorical and political party is categorical. So definitely count data. Are these randomly selected? Maybe, kind of, yeah. Our questions on the test will be a lot clearer. Yes. Great job, Jillian. And is expected cell count met? No, met. Well, this is where we need to use jump. You can do this by hand. We talked about how to calculate the expected cell counts yesterday. We went through tons of examples. Check out yesterday's lecture where we went through and calculated expected cell counts by hand, and we did so many examples. We might have it more open down here in the sheets. Where do we have it? We're doing it here. Here we go. Here's some calculations. Here's yesterday during class where we calculated all the expected counts and all the cell chi-squareds. It's a lot of work to calculate all the expecteds. To calculate one singular expected, we're talking about type of car someone has and their role at our company. If you want to do an expected count, it's row total times column total over grand total. And this mathematical equation would solve to this. So do remember this equation in red I'm drawing right here. Row total, it's on the sheet anyways, times column total over grand total. We put it on the equation sheet for grand total. And let's go take a look. This is something we should know how to solve. The row total is 35. The column total is 55. Divide by 150, and we get 12.83 right there. And that is the expected. It's a lot of by hand math, yeah. Doing it like once is worth it, and then you never do it again because you don't need to, because we got jump. And this is where jump's going to be a huge, huge help for us. So let's go over here and let's take the data, and we're going to go to copy to clipboard. With copy to clipboard, we've got it. Hit Control or Command C. So we've got this copied. We're going to hit done, and then we're going to go over here to jump, and we're going to go to a new data table with File, New Data Table. So make sure to copy the data and then go to a new data table. With the new data table open, we're good. go to Edit, Paste with Column Names. So there were column names like headings to the columns. And with the column names already on there, we're going to paste those column names at the top. Let's zoom in so we can see this a little bit better. So this here is someone's gender. This is the counts of political parties. The data is not quite in a format we can use right now. We're going to fix this up. So what we're going to do now, make sure it looks like this, pasted with the column names in there. If you pasted and it looked like this, you didn't paste with column names. So make sure to go to Edit. Great job, Jillian. Thank you, Jillian, for following along and telling me you got it right there. I just want to make sure I go slow enough and make sure everyone gets it. Because now we go to Tables and go to Stack. I'll pause on that. Take a little sip of coffee. Go to Tables and Stack. Under Table Stack, you'll click DR. It doesn't matter. Rock. It doesn't matter. You click DRI and we're stacking the quantitative columns. Doesn't matter what order you click them in. We just need the 3 quantitative columns right here. So once the 3 quantitative columns have been stacked, boop, you get a new table. Notice mine are in DRI, but DIR, it doesn't matter. Directory. Classic DOS right there. So now you'll notice we have the quantitative frequency right here of observations, and we have 2 categorical variables, which actually makes it count data. Count data is when we have the first group right here, and then the second group, and then the observations, the counts, frequencies of how many are in each group, like 31 individuals reported being male and Democrat, 30 individuals reported being male and independent. So now here's a big important step. We're going to go to Analyze Fit Y by X. Make sure you have this table right here with 2 categorical variables by the red bar charts right there and the blue, meaning quantitative. And once we go to Analyze Fit Y by X, we are going to pick the X variable right here that is going to be someone's gender. It doesn't say gender, but it is. And then we're going to pick the label as the Y variable, which is going to be, does gender explain label? And then big thing, make sure to put the frequency. Great job, Jillian. Make sure to put the data right here in the frequency. So this is super important, or else you won't get the mosaic plot the way it should look. And I do want to point out, we are getting a mosaic plot in a contingency table because it's 2 categorical variables. Categorical Y, that's what this represents right here. Categorical X, so we have 2 categorical variables. Trying to point in on this, that this quadrant of this graphic is mosaic plot contingency table are the main graphics we use. So you can see right here, we are going to get this graphic right here. Let's click OK. Make sure this exists, your data, or else it won't look correct. And here we are with the mosaic plot contingency table. Pretty quick and easy to see. More males are Republicans. Now, you don't need to do this, but I want to make this a little bit easier for you to see. Set colors. We're going to change this here to blue. We're going to change this here to red. And that makes it a little bit easier to see because in the U.S., going ethnocentric right here, in the U.S., Republicans are considered red and Democrats are considered blue. So it's a little bit easier to see that the males are Republicans. You don't have to change the colors. It just helps with interpreting the graphic. And the greens, like the Green Party, are independent. So males have a higher amount of Republicans. You can also see how many there are. There was 44.04% males who are Republican. And you can see there's more independent males with 27.52% of the males being independent. It looks to me like there is an association, but we don't do it by looks. Even though it looks kind of obvious there's a lot more female Democrats. You go down here to the chi-squared test of independence. Now, the null hypothesis was that someone's gender is independent of their political party. We have a very low p-value right here, which means we reject the null hypothesis. It means there is strong evidence that somebody's gender is not independent, i.e. associated with somebody's political party. Also, we have here the Pearson chi-squared test statistic, and let's review how that is found. Remember, if you saw the sheet I showed you, we found all of the expected counts. So you first have to look at how many individuals there are, known as the counts. That's how many observations we have, 48 females who were Democrats. Next, you have to use these observations to get the expected counts. This is where you do row total times column total over grand total equals this. Once again, be able to know how to find these using the formula sheet. We would go 92, because that's the row total, times 79, and that's the column total for this one, divided by 201. And there you go, that's how that number is found. So that is an expected count, and you'll notice here it says expected, so all these numbers are expecteds. Next, we would need to find the cell chi-squareds. The cell chi-squareds is the observed minus expected squared over expected. I'll write that in the chat so you can see it. That is observed minus expected squared over expected. So you have to take the observed of 48 and I'm just doing it for this one cell, minus the expected of 36.1592, times that by 2, there's the observed minus expected squared, divide by the expected of 36.1592, and there is the cell chi-squared. Have the counts, get the expecteds, then get the cell chi-squareds by the observed minus expected squared over the expected. Exactly. The cell chi-squareds are the squared difference standardized by the expected. Or do you see the formula right above Jillian right there in the chat? And Jillian, thank you so much. This is the big learning objective. So we're trying to like make sure by doing this we learn the big objectives. So great job, Jillian. Like see if you could get this number right here, this number of 0.91. Like you want to use these numbers right here. The observed is 30. This is where you practice to make sure you can do it. Observed is 30. And then the expected is 35.7015. Now you square the difference, observed minus expected squared, and divide by the expected of 35.7105. And then you should see this number right here. And we've done it. So that's really good practice if you're like, well, I can find these numbers by doing, it's the cell chi-squared. So it's the observed minus expected squared over expected. Observed minus expected quantity squared, like whatever you get when you do that. So now what do we do with all the cell chi-squareds? If we have all the cell chi-squareds, and I'll show you just the cell chi-squareds. If we have all the cell chi-squareds, what do we do with these cell chi-squareds, Jillian? And I'm going to show you in the background here for another 100 points. I'm going to do some not carrying decimals on these. Yes, perfect, Jillian. Oh, but no, the expected, you have 30 right there. It'd be 35.7015 because you did observed minus expected squared over observed. The second number is the expected. So observed minus expected quantity squared over the expected. So the denominator of that equation would be 35.7015. So observed minus expected squared over the expected. Yeah. Great job, Jillian. And then what do we do with all of these cell chi-squareds? So we would take all the cell chi-squareds, and what do we do to them? I'm doing it right now. I might not be carrying enough decimals. I'm kind of rounding and carrying. So what do we do with all the cell chi-squareds? Pretty close. What do we do with all the cell chi-squareds? We take all the cell chi-squareds, which are how weird each cell is, and then we get a total metric of weirdness for the test. Like, how odd is this test? And we call that the what? We add them up and we get the Pearson chi-squared test statistic. So the Pearson chi-squared test statistic is the sum of all the cell chi-squareds. If you add all these values together, which I kind of did, I didn't carry all the decimals, you will get the Pearson chi-squared test statistic. And then we have to ask ourselves, well, we need to plot this. This is the last step. We're almost done. So we have to ask ourselves, how many degrees of freedom does this test have? And it actually tells you right there. It has 2 degrees of freedom because this is a 2x3 table. And what is the mathematical equation to find out the degrees of freedom for the chi-square we're using, Jillian? Great job, Jillian. Jillian, I am throwing you 1,000 points. You're doing an amazing job practicing this today. 2x3 table, what's the formula for the degrees of freedom? If this is a 2x3 table, you got it, Jillian, and then we'll just drop each finger down. It'll be 1 times 2, which is going to give us 2 degrees of freedom. And that tells us which chi-squared we are using. We are using a chi-squared with 2 degrees of freedom. And we take the chi-squared test statistic of 12.28, and we draw this right here, and we do to the right, and there's the p-value. Am I blocking it? Just barely. So this is the p-value right here that Jump is getting. Jump gives a little more decimal place accuracy, but it's the area to the right of it, which seems very unlikely. We have to plot it on the proper chi-squared with the right amount of degrees of freedom. The degrees of freedom just show us the shape of the chi-squared because each chi-squared has a different shape to it. And notice how the p-value actually gets bigger because we have a different amount of degrees of freedom. So we have to put it on the one with 2 degrees of freedom. Just tells you what the shape is. The degrees of freedom tell you which chi-squared you are using or which t you are using. T and chi-squared have degrees of freedom. The normal does not. So that's got it. That's our answer. And we should have everything we need for the question now. Let's go take a look at the question. Is the expected cell count met? 2 seconds. Going to go see who that is. The joys of teaching from home. Expected cell count means we need each of these cell counts, expected cell counts, to be greater than 5. So this is met right here. If we go back to our expected cell counts, let's only show those. All of these expected cell counts found from row total times column total over grand total each need to be greater than 5. So please make sure how to review how to find expected cell counts. We were talking about this earlier, talking about how to find a singular expected. All of these need to be greater than or equal to 5. Technically the smallest one, but if the smallest one's greater than 5, they're all greater than 5. We show the equation up here, row total times column total over grand total. Jump will find all of these for you, but you should understand how to find them. And then the condition that each one of these right here, these are expecteds right now, need to be greater than or equal to 5. So we're good on that. And now we need to find the chi-squared test statistic. Great job, Jillian. And sorry about how to run off right there. I saw it ring at the doorbell. The chi-squared test statistic is the Pearson chi-squared test statistic. So Jillian is the Pearson chi-squared test statistic. Remember, the Pearson has your p-value. So we'd put what into the answer right here to 3 decimals. So what will be the answer for the Pearson chi-squared test statistic, which is the sum of all the cell chi-squareds? So if we found the cell chi-squareds, which are those values, they're the second ones, and then we add up all the cell chi-squareds, what will we get? Which Jump already does this for us. Oh, Wi-Fi's like, no worries, no worries. I'll answer it here in a moment. But right here, if we were to add up all the cell chi-squareds, we would get 12.28. This is the chi-squared test statistic, the Pearson chi-squared test statistic. Wish it said that on it. Whoops. So that's the Pearson chi-squared test statistic. Well, that's the p-value for the Pearson chi-squared test statistic. So the chi-squared test statistic, right? And so this is the good practice, Jillian. This is called the test statistic right here. That is the chi-squared test statistic. And then the p-value, which is the probability, is this right here. So the chi-squared test statistic, that is the chi-squared right here. And then the p-value for it, which is the probability of observing it, is this right here. Does that make sense? So the p-value tells us the probability of observing it. Yeah, so the chi-squared is like the sum of all the cell chi-squareds, and then we get the p-value by finding out how probable it is, and that's graphing the area to the right of it on the chi-squared. So we go to the proper chi-squared, and I think that's it right there. So we go to the proper chi-squared and graph it, and Jump does all that work for us. So pretty easy question right here. There's only 2 possible answers. Our p-value is lower than alpha. So will we reject or not reject the null? And not reject means fail to reject. Like I failed to go to the mall today. I didn't go to the mall. So will we reject or not reject the null? What will we do right here? Will we be like, I reject the null because the p-value is low, or I don't reject the null because the p-value is high, and I just let that null fly. I just let it be. We reject, definitely. If we reject, so think about it. They're like, I don't believe the null anymore. I think the null is not true. That's what reject means. They're like, I don't think the null is true. The null just doesn't seem likely to me. That's because you have evidence for an alternative. You're like, I don't think this person's innocent anymore. I think I have evidence of their guilt. When you talk about like court trials and stuff like that, we reject the null of innocence and we have evidence for guilt. So we're saying right here, we reject that there is not a relationship. I reject that idea of not a relationship here. I have sufficient evidence of guilt. And there we go. We got it. We found it. Let's go back here and look at the first question. We'll do a break in the video, do all the questions on the homework. Jillian, if you have more questions, let me know. We can work any question, homework, quiz, but it's your call. I'm going to work a few more questions, just kind of put them in the video here and tag the videos up later. But your call. Good stuff. Oh, man. It's almost break. Hope you're going to have a fun break, Jillian. I can't believe it. We've got like, including today, there's 4 days left of class. 4 days. Yeah, which number on the quiz do you want to do? Just be like, hey, can you do this one on the quiz and we'll do that? This one might be a quick one right here. Yeah, just mention one, or I'll do one of these questions, and then just tell me which quiz question to do. I'll do a quick first question on the homework. Let's do it. So there are some concerns about women who had an epidural to reduce the pain during childbirth. The drug can get into the baby's bloodstream. Oh my gosh, making the baby sleepier and less willing to breastfeed. So they're looking at were the babies breastfeeding if there was an epidural done. Yeah, break's gonna be awesome. And I'm gonna play some video games. So what kind of test are we gonna do right here? We're gonna do the chi-squared test of independence to see if is a baby breastfeeding after 6 months independent if the woman has gotten an epidural. So the chi-square test of independence, which has the null hypothesis that breastfeeding 6 months is independent of getting an epidural, which means, Rock,
it doesn't matter.
If the woman got an epidural, she'd be breastfeeding at the same rate, whether or not she got the epidural. And so continuing on, it says, what's the null hypothesis? The best one right here is independence. Yep, we already know the null is going to be independence. Great job, Jillian. So does it say in independence? There we go. Breastfeeding success is independent of having an epidural. Good stuff. And then the alternative would probably be not independent, but I think they're going to rephrase it. I like to say not independent, but that means there's an association. To say things are not independent means knowing the woman got an epidural would give you information about whether or not they're breastfeeding. Doesn't mean they will or will not. It just means maybe they're more likely. So, or less likely. There would be an association. Knowing they got an epidural would give you information, i.e. there would be an association. Which means not independent. Oh, that's it. That's the whole question. Just knowing what tests we're doing and the degrees for and all that good stuff. Hold back. No wonder no one's been asking about that one lately. Exactly. Not independent equals association. Exactly. That's what it means right there, which is the same thing as like a relationship, dependency. So you've got a lot of synonymous words right there. Like not independent means, see, the first semester I taught this, I just had my students memorize like independent, not independent. And then on the test, an instructor wrote a question that said something about association. And students like, well, no, that's not the null or alternative because it says associated. And I'm like, but that's synonymous. And they're like, you didn't tell us that. And I'm like, no. So now I try to make sure. Hey, Kayla, so good to see you. Kayla, we had Connor come by yesterday, and he was telling us about a package called Feather. Most pregnancies are full term. Let's do that. You got it. We're gonna do so. Really cool package. If no current student need any help, I'm having issues with TSibbles. Yeah, let's do that here next. So we're gonna do the question, and then let's load up the TSibbles stuff. You bet, Kayla. Thank you, Kayla. So Kayla, are you doing all the cooking for Thanksgiving? Or like, are you having family coming over? What's your big thing? If you want to share, what's your big Thanksgiving plans? This is the big topic of the day. I'm getting the next question loaded up and then we'll do yours next, Kayla. And Jillian's hanging out here. We're just all chilling out. More points in the chat. Put on a little chill music right here. What are your big Thanksgiving plans? I just put the turkey in the oven, or not the oven. Put the turkey in the refrigerator to defrost. Loading up this new question. Really, it was the last question. Wow. It's like, I wonder if it's there. Let's go check out this question. My husband has a huge family and everyone brings food to his aunts. That's awesome. That's awesome. I hope you guys have such a happy... Only 24 people this year. That's, well, only. I hope you guys have an amazing Thanksgiving. I hope that's tons of fun and everyone has a great time. And we're 53 at the... My gosh. That's so much food. So much food. I hope everyone has a great time. I hope everyone... Like, I don't know. I haven't seen my family in 2 years. Hopefully, I don't know. World needs to get more normal again. Let's go check this out. Most pregnancies are full term, but some are preterm, less than 37 weeks. Of those pregnancies that are preterm, they're classified as earlier than 34 weeks and late 34 to 36 weeks. That's not late. It's like normal, right? I don't know. I don't know a lot about pregnancies. A report examined those outcomes to 1 year, broken down by age of mother. Is there evidence that the outcomes are not independent of age groups? Thank you so much. Yeah. No, I want to look at this TSibbles stuff though. I love the FPP3 stuff is a lot of fun. So the null hypothesis. Oh, we got it. ABCD. What do you think, Jillian, right here? ABCD. We got to do our practice. We got to say like somebody's age is something of how long their pregnancy lasts. Somebody, which is called outcome. Somebody's age is what of their pregnancy lasting. That's the null. We always just put one word. We're doing the chi-square test of independence. So we always just put one word between this when we write it out. And then we kind of know some synonymous ways of talking about it is what we're talking about. So whenever we write the null hypothesis for the chi-square test of independence, we just say somebody's age. I think you're right. Yep. Somebody's age is independent of the outcome of their pregnancy, and somebody's age is not independent, which means there's oh my gosh. We're not doing check questions right now. That should be right. We were doing a homework a moment ago where we were checking the question. It just jumps into it and says, compute that chi-squared test statistic. Now, This is where it's going to be a lot more difficult if we don't use jump. So we're going to use jump. So what we would have to do, we're going to copy to clipboard. So make sure to copy to clipboard. I'll pause right here so you can copy to clipboard. If you had to do this by hand, yep. Great job, Jillian. You're totally right. And so if you did this by hand, Jillian, you would have to take all the counts, get all the expecteds, get all the cell chi-squareds, sum up all the cell chi-squareds, get the chi-squared test statistic, find the degrees of freedom, find the p-value, and then reject or not reject the null. We go through these steps during class, so make sure to watch class if you want a step-by-step process. But we next need to get the expected counts, but you don't have to do this if you can use jump. So we've copied this right here. We're going to go over here into Control N, or let's just do File, New Data Table, and Jump. File, New Data Table, and Jump. And so with the new data table right here, we're going to go to Edit and then Paste with Column Names. So we paste with column names the new data. And so we almost have it ready to go right here. And pause on the screen, take a little coffee. So with the new data inside of Jump right here, we're going to go to Tables. And we're going to go to Stack. With the tables stacked right here, let's click Tables Stack. We're going to stack the blue quantitative columns. So these blue quantitative columns are basically going to be put. Stack means you take a column, you've got columns right here, and you stack them on top of each other. So these columns are going to get stacked. Let's click OK and stack the columns. Boop. And now we have two categorical variables. Let's call this, I'm going to make it look a little bit nicer. Why not? This is like someone's age group, and this is the outcome. So we can double click that and call it age. And then we can double click this and call it outcome. There we go. Got it. Nice job. And you don't have to change the names of those, but it can make it look a little bit easier. And so now we know people's age and the outcome of their pregnancy. I don't know whether there should be early or not early or late. Let's go to Analyze, Fit Y by X. With the Analyze Fit Y by X, we're going to look at the two categorical variables to see if there is an association, i.e. they're not independent. And let's go here to the Fit Y by X now. Now make sure you see if somebody's age explains the outcome. Remember, age explains why someone has a certain outcome, but do not forget the frequency. I want to just pause on this and say, do not forget the frequency like that. Don't forget it. If you forget the frequency, the graphic will not look correct. So do not forget this. Very common mistake. Let's click OK right here. And so does this look associated or not associated? Yes or no, Jillian? Does it look like there's a strong association here or no? So when you look at it, we're looking at, here's the people who are over 40, a little bit more early term. Here's the people under 20. Here's the people 30 to 39, my age group. I'm in my 30s, not for long. And here's the people 20 to 29. Does it look like there's an association or yes or no? What are your thoughts on this? Just visually looking at it, which is not how we do statistics. I say that, and then visualizations are how we look at a lot of things. So visually looking at it, does it look like there's an association or non-association? It does not, I agree, and you are totally right. 100 points again, Jillian. You actually were able to look at it and see there doesn't look to be an association because Rock, it doesn't matter. Majority, the differences here between these groups are probably just due to random chance. And so you're right. You're talking about this width right here, the heights of within each group. So within the over 40, the early term is, if you can read that, 33%, where the under 20, there's 31%, 32% basically. All these percentages, like 27, that's a little bit lower, but they're all within about a few percentages of each other. So, and why does this look like this, Jillian? Really quick question. Why is this right here looking like this? What's the deal with this? Why does this look so small right here? And the answer is kind of over here if you look at the data. Why does this look so small in terms of width across here, which is not a bivariate thing? And by bivariate, I mean it's not a two-variable question. Why does this look so small right here? And the answer exists kind of in this area. So this would be that number, and then this one down here is that number. So exactly, Jillian, perfect, Jillian, great answers today, amazing work. There's just less individuals. You're looking at the univariate display. That's the marginal display, going back to the very beginning of the course. The marginal display of people's age groups, and there's less people in the over 40 age group. You're looking at the marginal display. This is just how many people had late term or early term pregnancies. And it's kind of neat when you highlight it. You can see it's showing you these are all the early term pregnancies and these are all the late term pregnancies. And this is just a univariate display of one variable. If you go in here, you're doing bivariate, like of the under 20 people, how many of them had late term, and you can literally see the answers over there, which is kind of nice. So I like to show both of them. So the answers are down here on the bottom of the screen. The chi-squared test statistic is 3.046. And once again, we'll show it just so we can show everything. The chi-squared test statistic would be the sum of all the cell chi-squareds. We'd have to first find every single expected and then find all the cell chi-squareds and sum all the cell chi-squareds. So the sum of all the cell chi-squareds would be this value right here, 3.046. And look, they're very tiny. Those are all very tiny cell chi-squareds. So you get this number here, which is not that big. Then you have to know to plot it on a chi-squared with 3 degrees of freedom, because this one's more complicated. It's a 4 by 2. If you notice, there's 4 here and there's 2 over here. 4 by 2 means 3 degrees of freedom, 1 times 3. Rows minus 1 times columns minus 1. And so you go to the chi-squared with 3 degrees of freedom. We're just showing all the steps right here. And then you go and you put in your chi-squared value of 3.05, I think it was about, and there's the p-value of 0.384. All this work is being done for you right here. 3 degrees of freedom. Great job, Jillian. Yep. And so all the work is being done down here to get you the p-value, which shows you that these results are likely. Like the differences we see between the groups are likely just random chance. It's like, I don't think anything's going on. It's like, yeah, sometimes this group has a little bit more, sometimes this group has a little bit less. I mean, it's just random. Like, this is the best way to think about it, Jillian. Like, I always try to tell people this. Let's go out and play. You ever play basketball, Jillian? I'm horrible at basketball. You ever play basketball? Like, do you ever go out, just shoot some basketballs? I'm horrible. Really bad at it. And if you think about it, if we said, let's shoot 20 free throws. And so you shoot 20 free throws and I shoot 20 free throws. You make 11 and I make 10. Now, you did better than me. Well, good. We're both awful at basketball. We're shooting free throws. And so, or layups. Layups are really easy to make. Well, you make 11 and I make 10 out of 20. So if you made 11 and I made 10, the differences between us would probably be what? And look at this right here. We can actually run the statistics on this. So we could literally go right here and go player. And we could go here, outcome and frequency. So Brian, Jillian, and make, miss. We can literally run the statistics because we're nerds. And so, Jillian, does this make sense? You made 11. I made 10. So we can do the same analysis we just did where we look at the player explaining the outcome. And we see here, there's the differences. So Jillian made more than Brian. But the differences between Brian and Jillian are probably due to what? Like when you look at these differences between us, the differences between Brian and Jillian on how much we made in our basketball. This is why you can't gloat. This is why you can't be like, oh, I'm better than you, Brian. I made 11, you made 10. I'd be like, well, that's probably just like because you got lucky. We actually know these things in our mind. Like if someone's like, I made 11, you made 10, we're like, well, yeah, you beat me, but maybe I'd beat you on a different day. Like maybe I would win if we played again. But, and this is what I love about Jump. Jump has a really cool thing here, the automatic recalc. I'm sorry about that. With automatic recalc here, watch this. Jillian, your skills are actually way better. We underrated you. Jillian, you actually made 18 out of 20. So now take a look at this. So now the differences between us are unlikely due to random chance. Does that make sense here, Jillian? The differences between you and me are now super unlikely due to random chance. Because if you made 18 and I was 50-50, so you made 90% of your free throws, or layups, whatever we're trying to make. You made 90%, I made 50%. And I'm like, psh, that's just due to random chance. You're like, no, these are pretty big differences now. Like these differences that you see between us now are unlikely due to random chance, Brian. The p-value tells me that you making 50% and me making 90% is very unlikely. So if you made 2, if you only made 2 out of 18, so now I'd probably be better right here. Is it not going to change? There it goes. It updates now. So now, and it's very similar, sort of same way, but in reverse. So now the differences between us are again unlikely due to random chance. So you'd have good evidence that there is an association between the player and how good of a free throw maker they are. So now there is strong evidence of an association. It doesn't mean Brian will make free throws. It means if we know if Brian is making the free throw, he's more likely to make it. Like there's an association between the player and the outcome. And just I don't know. Hopefully that makes more sense. I like to hopefully bring this into like, well, what does this all mean? What are we trying to learn by this? We're trying to see if knowing X tells us something about Y, which is very important for making decisions. So we have all the answers we need right here. We've gotten all the data, and hopefully the examples make it a little more clear. We want that chi-squared value right here. The chi-squared is the sum of all the cell chi-squareds. The p-value is the probability of our results or results from our extreme happening by random chance variation, given the null hypothesis of there being once two. 3 decimals there, good. And then, so Jillian, is the p-value high or low? This is where we reject the null or fail to reject the null. Is the p-value here high or low? Your thoughts? And then, Kayla, we're going to work on yours next. Thank you, Jillian. I like to, just think about it, like, how could you use this stats? I mean, you can use it for research all the time, but how could you, like, go to a basketball court and show someone you're better statistically? Like, you can say, statistically, I'm better than you. That's when they just yell nerd at me and I run off the basketball court. P-value here is high. Oh, that is a high p-value. That's woo! That means if someone told you have a big interview and you're like 40% chance of rain today, you'd be like, I'm going to bring an umbrella. This is a very likely event. And so the p-value is greater than, there's not evidence for alternative. The p-value is greater than the level of significance. We do not have evidence to reject the null. We cannot reject the null. That should be correct. It's a lot of words. Just to say the p-value is high, we don't reject the null. We don't have evidence for the alternative. So remember, when the p-value is high, just let that null fly. When the p-value is low, reject the null. P-value is low, reject the null. P-value is high, just let that null fly. Just let it be. Don't reject it. Just let it be. It was Amazon delivering me a package. Oh no, Hoopa's latest adventures are coming to an end. No! Drop those questions in the chat. We're going to hop over to the main screen. I am so sad. Thinking music. Let's get ready from some TSibbles. Time series TSibbles. Hopping over to the main screen for some TSibbles. Let's do it. What's going on with computer making noises? So we're loading up some library FPP3. Connor yesterday was talking about the Feather package. I need to read more about Feather. I was going to take a look at it here. Gotta remind myself later. Got the final there for 320. So when we make TSibbles, what we're going to do is we're going to take some original data. I sent you a Discord pic of the arrow. Oh, cool. Let's go take a look at that. 2 hours later. Let's go take a look. Oh, yeah. So the data tables get super mad about this. It's the shiny with the data table with the TSibble. Okay, I see this. Yeah, Connor was talking about Feather yesterday. I need to explore it. I like that you have a list of packages to explore. Like GG Easy I want to look more at over break, and Feather I want to look at in recipe. And there's actually a really good data scientist at R who I'm hoping we can get on here to interview. I need to set these things up over break, make like a Friday series or something. Like I think that'd be really good and helpful for students to have like a Friday interview series where we do like, I don't know, 30-minute interview and like 15 minutes questions or something. But there's a bunch of really great programmer people. We got Seattle Data Guy. I've got a bunch of people who said they're like, yeah, I'll do it. I seem open to it. And then we need to set up some interview stuff. I need to make some cool new backgrounds. So this is actually a shiny issue. Yeah, TSibbles really help with that because you get into a lot of the piping. So my students have been using the Nestle data a lot. It's actually a thing from Seaver. I don't have the Nestle there. Is it lowercase? Where's the Nestle file? Where's that Nestle file? Let's go grab the Nestle file. I swear I got the Nestle file on here somewhere. Am I not in downloads today? Nestle new. I've got a Nestle new file. Nestle new. There's Nestle new. So sometimes you run into issues with the missing data on the last like Y observations, but let's take this and go here and store it as Nestle. So we have a data file that we're loading in, And so what we want to do now, I'm going to make sure I get this down, is we want to take our data file. I always cheat and look at the book, but I'm going to try to do it from memory so I'm not cheating today. We want to mutate. And so mutate can be used to add on a new column. See, everything, there's the volume in millions right there. We want to create, because can't we just create a variable like the year month function? I'm trying to think here, Kayla, right? Because we want to take first, before turning into a TSibble, we need the key variable, or the index variable. Keys are how you split it apart. Index is what it needs. It needs an index for a TSibble. So the index right here, what if I do this? I don't like that name of that first column. Let me change that first column and change it to date. So names, let's go here and change it to date. Good. Looks like date. Mutate, let's do date equals year month on date. And there we go right here. So it's doing it at 1970, but can we not add a start to this? How do we use the year month function to get a start on it? Don't want that. Because shouldn't we be able to set month unit? Oh wait, unit? I don't even know what unit does. Sep equals, whew, Kayla. Holy mackerel. Oh, Kayla, can you send this? Can you put this on Discord as a drop it on Discord real quick? Put it in the parentheses, or the backtick, mutate and unite. Drop that on Discord real quick for me, so that way it because I'm assuming you probably have it like formatted a little bit more. Drop it into Discord. I'm gonna see here about this if I can do a. See, they're doing a sequence right there, which I've done the sequence to set it up. I just want the year month to choose a starting date. Like, it is there. Awesome. Let me go grab it. It's the jump right there. Thank you so much, Kayla. Yeah, and that's what's so good. This right here. Yeah, so nice, so nice, so nice. Already formatted. Great job. Kayla, 100 points. Segment file. So you're talking about this is the file we're piping in. Do I have everything? So you're taking the month variable. I don't have a month. I do have a month. Month, and you're taking the year and the month. You're putting a sep right here. So you're uniting those. Is that a... Okay, cool. So there it is right there. That's creating that. Wow, I've never used unite. So unite is unite like you're overriding month with year month. Was there a year variable a second ago? There is. So it's taking both of those and creating, so it's uniting them. That's what unite does, is it creates and makes a new column out of those. Oh, that's cool. So so you are creating, so it removes out the one. So year month becomes a new column. Like if we call this like new date or something like this, this will now create a united column. Oh, is it mad? Does it have to unite on one of those, or did I just type something incorrectly? It might have to like choose the one it... No. There it is. Okay. So the unite is helping me to create the date column that you already had. Exactly. So unite is... That's such a... And that looks like a dplyr file. Obviously, we're pumping it, piping into it. So it's going to take the original columns right here, choose the separate right here, the sep argument. What is the default sep? I'm going to let it run default sep on this. It's an underscore. Okay. The default sep is an underscore. Yeah, definitely. This is, I love this. And then we're going here to, I'm calling this, so this should work right here. Kayla, you are a genius. Ooh. What's going on right here? I'm gonna change it back to where you had it as month, so we'll overwrite month. Oh, you see, now I'm getting this error, Kayla. Oh, because I have a new date. Don't watch me. I like making errors. So right now, the date. So you'd not be able to use the mutate on your original day because you already had a column that has the combined month and year. Well, so we have this right now, but the problem is this is yours coming out as, which this should key equals segment name. Yes, the segment name right here. Well, no, we don't have a key on this. There's no key variable. I mean, I guess you could key by year, but we're not going to key on anything. And oh, you know why? The duplicate error is coming from this. The way it's making it right here. Oh, you know, yeah, I think you're right there. So if you look at the table, the reason it's mad about this is the duplicates. And I don't know why the way this is right here with the ones, it's registering this as, oh, look at it. Everything's the same. Oh. Okay, year, month. The way it's registering it is it's repeating 1400 Jan. So is there a month year? No, there's not. Let me reverse this. I don't know if this will fix the problem. Okay. Didn't fix the problem. Let me look at what's running through. Oh, we don't need the unite? Okay. My day is different than yours. So, and I'm just seeing right here. Do you see how it has like Jan, blah, 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 blah? What I want, if we're saying like, let me try something, right? Click on this, Kayla. Let me remove this off for the moment. It doesn't like that. Well, it just won't run that, will it? My issue is with the mutate, the year month aspect of it causes me issues when creating. So the data tables have a hard time display in the, and this is something we need to look into. So if you get answers to this, tell me too. But I think data tables have a problem. You won't be able to use the data table package to display a TSibble. The TSibbles don't like to be displayed in a data table. Does that make sense? So you have to use like a regular table or other packages to display it. But the data tables don't, or the TSibbles don't display in a data table. And I need to probably, if I don't know if Ron Heineman wants me to email him about it, but the TSibbles don't display in a data table. We found that out the hard way. A lot of people running into that error. So we had that growing pain right there. Right now I have the issue that it's got the wrong date and it's got duplicate dates. So it's doing, so it's got the, and then you see that, but it should be registering. Yeah, I think you're right with the way my data is. Like I probably don't have to unite it. So mine looks like this. I'm going to go here and go to mutate. I'm going to go to year equals year plus 1900 or 1980. We're going to set it to the start of 1980. Cool. And it's year month, right? Okay. So that's good right there. We're going to pipe it through that. We're going to pretend this starts in 1981. And then we're going to pipe it through another one. And then we're going to mute. We're going to unite. I'm going to use your unite column right here, Kayla. I'm going to go to date equals concat. Wait, no, date, comma, concatenate year, comma, month. And so, and I'm going to do a sep equals a space. And I think that should work. And then I'm going to take right here and mutate. I'm going to mutate the date to be year, month of date. Good. So Kayla, we got it going right here. Yeah, data tables are pretty awesome. And so I think this has done it right here. And Kayla, this unite code, Kayla, thank you. This unite code is pretty awesome. And just seeing how it works right there with the arguments of where is it being stored? What are we bringing together? And where are we separating it out? And so we could probably do is we could probably go in here and go to a select. And let's go to a select in here and go to date and volume in millions. And there we go. There's our table. And so we got those things. And then let's go here to as TSibble. And it's just good practice. The more you do this, better you get at it. So even I got to practice. Index, date, and there we go. Boom! There's our TSibble. And of course, last but not least, you got to store it out right here. And let's go to Nestle TSibble. And there's our Nestle time series. So we should be able to take Nestle time series and go to auto plot. Don't fail me now. There we go. There's the time series of it. Is there an issue or just a me issue? Do you know why using the TSibble method is making my app run slower compared to the app I created using the TS? You would think that it would be faster because dplyr is supposed to do that, right? You would think. Good question, Kayla. You could send it to me and I could try some runtimes on it. But you would think it'd be faster. I mean, this is good stuff. I wish we had Rod Hindman on the line right here. It's his packages. It's all the Hadley Wickham packages. But there's a really great data scientist in ours, last thing, and then we'll hop over to Jillian's question. I want to see if I can find that data scientist in ours page again real quick. Let me go to my YouTube. But she has such a great channel. Let me go to my subscriptions. I'm on my YouTube channel here, and so I've got like Seth Bling, Phil. Like, it's funny what I'm subscribed to on this channel, but she now put out a video lately. She's got such a good, this is all. It's basically Philip. I'll show you this. My subs on this channel. My subs on this channel are like all data science and Philip DeFranco. So you got different data scientists here. You got this guy. He's really great. Where is the? Am I not subbed to her on this channel? This guy is a guy at UT. He makes really great videos too, showing stuff. Seth Bling, great stuff, Seth Bling. Like Alex the Analyst, great stuff. Seattle Data Guy, and just all different things right here. Spider-Man, love it. Let me go see if I can find it. Looking through all these people talking about our data scientists. I guess I'm not subbed her on this channel. Take just a moment here. I'd like to reach out to see if they would appear on the channel. Maybe. Did they leave their channel? Wow. Hard to find their channel. Okay. Let's put 1 minute on the clock, and if we can't find it, we're going to head back over. 1 minute on the clock. Can't find the thing I'm looking for. That guy's doing exactly what I'm doing. A lot of R videos nowadays. Wow. Seattle Data Guy everywhere. Well, looks like it's like how to learn R in under 2 hours. I'm like, man, if you can learn R in 2 hours, that's amazing. Well, I'm bummed. I don't know why I can't find. Okay. Well, no, I don't want to switch channels. If I switch channels, I might lose it. Well, I will try to find them. That's our 1 minute. We'll try to find it. Let's go to Jillian's question right here. Certain war story. Let's head back to the main screen. I really wanted to find that. I really wanted to find their channel to showcase it. But we'll have to find that another time. But TSibbles, great stuff right there. Let's check out that certain war story. Certain war story. Here we go. There's 2 certain war stories describing several weeks of a long war. Here we go. Let's go check out the certain war story right here. Head over to the main screen. War story time. Run those models. Let's check out. So here we are. We've got what happened in this war. We have, was the injury lethal? It was fatal or not fatal? Fatal. And where was the injury site? The body, the head, the neck, or the limb? So with these right here, we see the counts of the observations. So this is count data. Yay, war story. So we have 118 fatal injuries, 32 non-fatal, body injuries, head injuries, neck, limb, all these injuries. The null hypothesis is going to be that the two are independent of each other. And the alternative would be that they're not independent. That's because we're doing the chi-squared test of independence. Great job, Kayla. Anytime. Anytime. So that is the first answer right there. Remember, it is the chi-squared test of independence. Now, you could work all this out by hand. I highly suggest doing at least one by hand or practicing how to get the expected counts right here. You see an example of the row total times the column total over the grand total. So we could find one of these. To find the top one right here of 62, so we take the row total of 68, I'm not blocking it, good, times the column total of 118, divided by the grand total of 150, and that right there is the expected count, 53.49. Oops. Now, finding one's just good practice to know. Great job, Jillian, right there. You know how to get that expected count, row total times column total over grand total. Jillian, I'm throwing another 500 points. You are doing so much great practice today that when you get to these test questions, you will just ace it, and that's what we love to see right there. So I do want to point this out. You want to practice it just like Jillian's doing right there because, and these are the expecteds, good. We can do it in jump. We're going to go here to copy to clipboard. And once we copy to clipboard, we're going to hit Control-C or Command-C. So we've copied this to the clipboard right here. We're going to go to a new data sheet, and we're going to go to File, awesome work, File, New Data Table. File, New Data Table, anywhere inside Jump. File, New Data Table. With File, New Data Table, we're going to go to Edit, Paste with Column Names, because there was column names when we went to paste this, when we copied it first, though. So we're going to go to Paste with Column Names. Boom, we got it. And then we're going to do the same thing we've been doing. We're going to go to Tables, and then we're going to go to Stack, and this will put the columns on top of each other. Tables, Stack. With Table Stack, double-click both of the blue columns. This is going to take the quantitative columns and put them on top of each other right here so we can see the frequency counts in one column. Let's go ahead after the blue columns have been clicked and click OK. So now this is our final table product right here with where someone was injured and the outcome of the injury and the data right here. A little hard to tell. I think we need to put this, and we'll try it both ways. Why not? We're going to go to Analyze Fit Y by X. Hopefully we get our table to look a lot like their table. We want it to look very close to it. And with this, we're going to put the... Sure, take a shot. I'm going to flip it if need be. Let me see. Make sure to put the data in the frequency. That's probably the most common error is we need both categoricals up here and the data in the frequency. And yeah, that looks right. It's in the right order. Great stuff. Let me show you again how this was composed. It should look in this order. You should get this sort of thing right here with your label at the top, your column right here, and your data right here. Now, we almost have the answers we need. We want to take this and remove out using the red arrow all this extra stuff like the column percentages and the row percentages. And we really only want, at this point, the expected counts, which is how many we would have expected by random chance given the null is true. That's what expected means. Like, if there's no association right here, well, I mean, if you look, there's about the same amount of body, head, and limb injuries. So, well, there's a little bit more body injuries. So if you look at this, there's more body injuries. So I'd probably expect a little more fatal body injuries. And you see that right there. There's a little bit more fatal. There's a little less limb, so a little less fatal limb injuries. A little less limb, so or a little less head. I think I forgot the frequency or something. It says the period. Yes. Go to relaunch. So click the redo relaunch. So I'll pause here so you can see how to get back here quickly. And go to the redo relaunch. And then if you forget that you are correct, Jillian, you're following along perfectly. That's the error. A lot of people make it. Got it. I just redid it. And you can go right here and then you can add it back in. The redo relaunch is great. It easily allows you to fix errors like that. Don't worry. Very common mistake. Literally someone yesterday is like, like, what? It didn't work. And I'm like, wait, check this out. Because it'll be, yours was flat, right, Jillian? And does that make sense? If it's flat, well, then the levels don't really matter. So Jillian saw a flat graphic right here with a chi-squared of 0. This is not the right answer. I'm just going to show what we saw. This would be no association right here because it's very flat. And then the chi-squared is 0 and the p-value is 1 because there's no association. It's just completely flat, where this shows an association. If you're at war, crazy times right here. And so if you're at war, would you want to get hit by something in the body, the head, or the limb? Probably. None of these are great choices, obviously. But the limb is where it's least likely to be fatal. Just think someone who's hit in the limb, like with like spear, let's say. You get hit with a spear to the knee. So less likely to be fatal there, taking spear to the knee. Good stuff. And so if you get hit in the body or the head, exactly. So then these are the more likely fatal areas. But these are what we would expect by random chance, where the counts are what we observe. We observe, look at this. Oof. We observe a lot of people dying because of body injuries and a lot of people dying because of head injuries. We don't observe that many people dying unless you're Achilles. Yeah, exactly. Don't want to take a spear to the heel then. So you observe way more people than you would have expected in these areas, but you observe less having fatal injuries here. That'll lead to the chi-squared, cell chi-squareds. Let's take these numbers. We're just going to make it so we can see everything. And we really only care about the expected counts at the current moment. So we want to just show these expected counts. Once again, know how to calculate these. You notice the number right there, the 53.49 is what we got, and it needs 2 decimals. Tell me if you get a rounding error. I will give those back. Make sure it's close. Make sure it's close. Make sure the rounding error is very close. Like, Brian, I was 10 thousandths off. Obviously, yes. 9.81. And so then what do we use the expecteds to get next? We use the expected cell counts to get the cell chi-squareds. And the point of the cell chi-squareds is how weird is each one of these cells. And look, the really weird part right here is like people who get hit in the limb aren't dying. Now that's not weird to us because we know how things work in the world. But to this mathematical equation, it's saying we expected way more people who got hit in the limb to die, but we see like very divergent numbers from what we would have expected, because that's what a cell chi-squared tells you is how odd this is. And if you look down here, the 51, which is the chi-squared test statistic, it's the sum of all these cell chi-squareds. So if you were to add up 1 plus 5 plus 1 plus 5-ish plus 8 plus 30, you'd get 51. And that's the chi-squared test statistic. And so 51.202. That's the chi-squared test statistic telling us how weird is this full test? Like, how odd is everything we see? And everything we see is very odd given there is no association, given they're independent of each other. The p-value here is 0. I know it says 0.00001 here, but that's, if you hover over it, you can actually see it's ridiculous. Might be hard to see, but that says e to the negative 12. So that's 0.000000001. That's a ridiculously small p-value. It's basically 0. It's so far off the curve we can't see it. Because, yeah, we know that we reject the null hypothesis here because the p-value is way lower than our alpha, which is where we reject of 0.05. There is strong evidence to conclude that the site of somebody being injured and whether or not it was lethal are not independent. That means they're associated. Like, you would just say to your friends, like, yeah, if you get hit in the head, you're more likely to die than getting hit in the limb. There's a strong association. Yeah, that's super low. Be like, there's a very big association with where somebody gets hit and the probability of them dying, like whether or not they die. And that's all we're doing right here. We're just saying, you know, is there an association between where you get... Wait, did I not put in... Oh, how many degrees of freedom? This is a 3/2. So how many degrees of freedom? It's on the screen. How many degrees of freedom? This is a 3/2. So how many degrees of freedom? This is not the answer, but it's the mathematics. Rows -1 times columns -1. There are 3 rows, 2 columns. Virtue of 3 rows, 2 columns, 2 degrees of freedom. It's in the output. I was like, where's an answer missing? I love this chapter, Jillian. I think it is one of the easier chapters. Mathematics just is very consistent. I hope you like this chapter too. I find it to just be very, like, you do the steps, you see your observed, you get your expected, you get the cell chi-squared, you sum the cell chi-squared, you get the chi-squared test statistic, you find the p-value, you're done. And once you do it like 5 times, you're like, okay, so I need to find what would I expect according to the null. So let me look at how far away those are from the observed. So let me get the cell chi-squareds. Let me sum up the cell chi-squareds. And you can just kind of go down in the output. And then, okay, I need to graph my chi-squared to find the p-value. Is my p-value low? I reject the null. But hopefully testing and things like this are making some more sense. This is really one of the reasons, like these last two chapters are a lot of the same knowledge. It's an easier one, which is nice. When I'm always, yeah, exactly. I know, right? I think we're all just, I appreciate Jillian. I'm glad we got some work done today. We're going to head off here in a moment, but Jillian, thank you so much. Amazing work, amazing practice. It's almost Thanksgiving, but great work, everybody. Puppet Shark, you ready to take a break? And grab some lunch. We'll be back here. Jillian, swing by afternoon office hours. I might do short office hours. Who knows? Jillian, everyone's going to be thankful because Jillian, I don't know if no one showed up. I was going to be like, well, but Jillian, you got a bunch of work done. We got some great answers, and I really appreciate all that practice. No, thank you, because I don't know. It's just really awesome when I can tell, like, you're like, I got to get this down. Got to learn it, and then I'm going to have a great break. So have a great break. Enjoy. Keep up the great work. We'll be back later. Bye for now, everyone. Bye. Break time.